Let's talk now about inserting into a binary search tree. So I'm going to do this one interactively by modifying the slide, but the basic algorithm is similar to searching. So you search for the key, and if you find it, you don't do anything because it's a set. But if you did not find the item, you'll create a new node and set the appropriate length. So let's say I want to insert the word eyes. So I'll make a new box. We'll call it eyes. And the question is, where's it going to go? Okay. So to do this, we're going to search for eyes. We'll say, dog, are you eyes? Ruff, ruff. Nope. But I'm bigger, says eyes. So I'm going to go to the right. We get to flat. Well, eyes is not flat, so we'll go left. We get to elf. Elf is not eyes. And then we search to the right. And we see, hey, look, there's nothing. Look, there's nothing over here. So at that point, we'll take a new box, and we will point elf at it. Okay? And that's it. That's the whole process. So what might that look like in actual code? Well, this one, unlike search, the gap between the high-level kind of hand-wavy picture and the actual code is a little bigger. And let me just show you roughly what it might look like. Okay. So in this case, we have an insert method with an insert key. So to insert something, well, if t is equal to null, we're going to return a new tree. Now you might say that's a little weird, like I haven't changed a pointer, but we're creating a tree and then returning it to someone. Well, who? Okay, well that comes in the recursive calls. So if the insertion key is less than the current key, jeez, let's fix some typos in the middle of the lecture, it's no good. Anyway, if the insertion key is less than the current key, that's for example, we're looking to insert eyes and we're at flat. In that case, we're gonna insert into the left tree, and we're gonna say t.left equals insert t.left the insertion key. So it's a little strange, right? Like flat is going to be setting its left pointer to the result of an insertion. If the insertion key is greater than t.key, we'll do the opposite. We'll say t.right equals insert t.right ik, and then lastly, we'll return t, if none of these things is true. So in other words, if the insertion key equals the t key, we'll return t. So maybe one way to think about this is there's two ways that we don't make a recursive call. One is we fell off the tree because it was null, and we return a new node containing the insertion key. The other is that the key is already in the tree, and we're just returning a link to the existing node. So these two non-recursive calls basically will refer to the item. And this right here, the fact that each of these recursive calls is saying, for example, t.right equals insert, this is important because when we get to elf, we need to say t.right equals the result of inserting on the null side. Now this is a little mind-bending, and I don't actually expect you to understand that having me explain it to you right now. And that's what the lab is going to be for when it comes to completing this exercise. Now what's funny is this code, I mean, this is the right way to do it. It's really nice, but a little alien if you haven't written code like this. By contrast, I know that many of you will be tempted to write code like this, and this is my main warning for this lecture. You might be tempted that the code should somewhere contain, if t.left is null, then t.left equals new binary search tree with the insertion key. Otherwise, if t.right is null, then say t.right equals new binary search tree. So you could write code like that, but that is a really bad rookie mistake. It leads to more complicated code, and it's just not as beautiful and elegant and as efficient as the nice way. We have to learn how to think like this in order for it to work. This right here, I call it generally arm's length recursion. You're not really trusting the recursion to do its job. You're saying, well, over there, if it's dangerous, I'm not going to go there. I'm going to avoid the danger altogether. I'm not going to trust some base case. And that is a very common issue when people are new to recursion because it's like a little more natural at first. So avoid this when you actually get around to implementing the insert operation, and instead use the approach I'm pioneering in pseudocode on the left. Now again, I have to say, this is a pretty tricky concept, and I don't expect you to fully digest it until you've actually worked on it on the lab. All right, so that's insertion, and it'll take some time to digest, but we need to address one more issue, that of deletion.